Welcome to the picture language seminar. So we're starting half an hour earlier than we did in the past, and I hope this message propagates. The people here know it, but I hope the others who want to come will realize that too. We're very happy to today have Zhengwei Liu talk. Zhengwei, many of you have heard him talk before. He's a wonderful mathematical physicist, mathematician, and physicist. He's responsible for starting the quantum Fourier analysis, the study of Fourier analysis on quantum symmetries. We've heard him talk about that before, but he has interesting new results extending to Neumann algebras, and I hope that we'll hear about that today. So Zhengwei, it's really nice to host you in this talk about quantum Fourier analysis on quantum symmetries. Zhengwei, go on, share your screen.
Thank you, Arthur. It's great to see many friends again and to present this new work at Harvard. And actually this year I talk about quantum Fourier analysis for maybe about 20 times. And there are two reasons. First, we have some breakthrough on this topic and we want to present that. And second, I was involved in some administration stuff and I didn't have enough time to prepare for a new talk. But this time I do prepare for this new talk and it takes a bunch of hours, but I think it's good to present something new at Harvard. But still for the first half of the talk, it's not really new work, but we collect interesting results together to set up our original motivation. Essentially, this talk is inspired actually by two works. One is the uncertainty principles on subvector, a very important type of quantum symmetry. And we have been working on that for a while. And another motivation is a recent work of Widgerson, Widgerson and Widgerson. They also work on uncertainty principles using another method called Harmonic Matrix in a unified way. And somehow we compared work and we saw, okay, there is actually a more general way to view the two topics and combine them together and to study quantum uncertainty principles on those quantum symmetries in a very general sense. So that's the main idea of the talk. And we will reach to that at the end. But first, I will explain. And I will start with classical symmetry. By classical symmetry, we mean group symmetries. And then we will go to quantum symmetry and see the uncertainty principle is actually robust. It's also true on quantum symmetries. And then we will view several examples about this phenomenon. So first, let's talk about uncertainty principles on groups. The story on the Fourier duality goes back to 1800s. And when Fourier introduced his transformation, he attempted to solve differential equations describing heat. And then he wants to describe the function and decompose that as sum of sine function and cosine functions. So he introduced this transformation from the ordinary basis to the Fourier basis. And that's the Fourier transform. Well, for the Fourier transform, first it's written in terms of this integration. We take the function and compute its inner product with the sine cosine functions. And this integration formula is good so that we can easily do analysis. And we'll see that soon. And a very important property of the Fourier transform is that it intertwines the two important operations. One is the multiplication of functions, and the other is convolution of functions. So for the convolution of functions, that remembers the group structure. Here, the underlying group is the real line. So actually, if we just look at the functions on the reals, we don't remember the group. But if we also remember this convolution, okay, then we remember the group. So to capture the full data of the group, we can start with the space of functions on R, and remember that algebra in two different ways. One is the multiplication, and the other is a convolution. And we have two different algebra, and the Fourier transform intertwines the two. So that data will remember the group in full. And another important fact is the Fourier transform intertwines two operators. One is the position operator to multiply the function by x, and the other is the momentum. That's the first derivative. The Fourier transform intertwines the two, and that's the fundamental idea to solve differential equations. So we change the differential equation to polynomial equations, and then we understand that much better. And to run the analysis, first we need to consider measure. Instead, in addition to the algebraic structure, we also need to learn the measure. And on the reals, the natural one will be the Lebesgue measure. And when we take a measurable function, we can define the p norm in the usual way. So we take the function value to p's power, take the integration to 1 over p, the usual p norm. And this is a norm when p is bigger or equal to 1. It's not a norm between 0 and 1, but we can still define it in this way, even though it's not norm. And the infinite norm is the essential norm of the function, essential maximum of the function. The Fourier transform has a good algebraic property. It preserves the two norm, the L2 functions. Using this property, actually, one can define the Fourier transform on the dual. So if we take the space of function to be smaller, like Schwarz function, then the dual space will be bigger, considered to be general function. So we can define the Fourier transform in a more general way. But in this talk, we don't make a distinction between different space of the domain. We just take a good function to establish the general idea, say Schwarz functions. And then by interpreting, first we can use the integration formula of the Fourier transform to set up this basic inequality. The infinite norm of the Fourier transform of f is bounded by the one norm of f. And then by interpolation, we can get the inequality between p norm and q norm, subject to the condition p inverse plus q inverse equals to 1. So this is the well-known Hausdorffian inequality. There's another important story related to this Fourier duality, and that's the driving phenomenon of this talk, this uncertainty principle. In 1927, Heisenberg first shown that in quantum theory, that the position and the momentum cannot be simultaneously measured precisely. So this is a fundamental phenomenon in quantum theory. So in that sense, if we want to describe the wave function, it's actually a density matrix, and the measurement depends on the basis we choose. So if we choose the x, the position, or if we choose the dual basis for the momentum, then the two corresponding two operators are non-commutative. So that will lead to an uncertainty principle. And this phenomenon has been mathematically formulated by Kernot and by Weil in the following way. So we take the two operators, and then we compute their standard deviation that has a lower bound, non-zero lower bound. For physics interest, usually we put this Planck constant. Mathematically, we can renormalize the scalar, and we write it in the following form. So we take a function f and take the position operator xf and compute in two norm. Then we take the same function f and compute the pf, or the momentum p, and compute two norm. Their multiplication has a lower bound. That's a precise mathematical formula. Now there's another way to read the formula using Fourier duality. So we consider this pf as x multiplied the Fourier dual of f. So we look at the same formula but in the dual space. In this way, we have a pair, one is f, the other is the Fourier dual of f. And then we can compute the standard deviation, and we get the lower bound. And this is the Heisenberg uncertainty principle. And later, Hirschman realized that there is another way to study this uncertainty principle in terms of entropy. It's the Shannon entropy. Given a function, we can compute its entropy. So this can be regarded as a function, fx, a wave function, and now we look at density metric. So it's the absolute value square. Well, here it's much easier. It's just a positive function. It's not even a matrix. And then the entropy is defined by this function calculus minus t log t, and then we take the integration. That defines the entropy. And he showed that the entropy of f square and plus the entropy of the Fourier transform of f square has a lower bound. And actually, this can be easily derived from the Hausdorff inequality. We can just simply take the derivative of the Hausdorff inequality at p equals 2, and then we get this entropic inequality. And then Everett conjecture that the lower bound is actually log e over 2. So there is a beta constant. And this follows from a deeper result of Beckner in 1975. He gave a sharp Hausdorff inequality. So he improved this beta constant in the Hausdorff inequality from 1 to a of p, s of p. And by taking the derivative of this optimal Hausdorff inequality at p equals 2, we can have this beta lower bound log e over 2. So this is a very important entropic uncertainty principle. And actually, this uncertainty principle is stronger than the original version, the Heisenberg uncertainty principle. The reason is that we can take an exponential map on both sides and then compare this entropy, exponential of the entropy with the standard deviation. We can get the inequality directly, independently for f and the Fourier transform of f. Then we can get the previous inequality. So somehow this entropic inequality is a stronger one. And in the same year, 1975, the two physicists, Yanqi, I'm not sure I give the right pronunciation, and Birula, they gave a physical interpretation of this entropic inequality. And there's another important fact about those inequalities, like Hausdorff inequality, the entropic inequality, that the extreme measures of this inequality are given by Gaussian functions. So we know Gaussian functions are very important, and actually they're closely related to those inequalities in Fourier analysis. And then several years later, Dontahue and Stark in 1989, they started another type of uncertainty principle for finite groups, and first for cyclic groups. So given a non-zero function of cyclic group G, we can look at the support of the function, namely the cardinality of the positions that takes non-zero values, and also the support of its Fourier transform. And then the product of two supports has a lower bound, that's the order of the group. And this kind of uncertainty principle is pretty interesting. And this has been generalized to other group symmetries, like from cyclic group to finite abelian groups by Smith in 1990s, and then Mesh-Lam on finite groups, and then by analogue and Russell on compact groups. And furthermore, this kind of uncertainty principle has been used in complex sensing by Candice Sternberg et al.
Zhengwei, we're losing your internet connection.
that happened quite a lot for idea free form, and that's the
So what happened?
okay.
Zhengwei, we lost you for a while.
Okay, so from which page?
On that page, and when you were talking about this Dontahue dark inequality, when you got down to the bottom of the page, we lost you.
Okay. So this uncertainty principle has been generalized to different type of groups, and it has been deeply used in complex sensing for signal recovery. And the key idea is that this inequality tells us that if a function is sparse, namely the support of a function is very small, then we can know this function by looking at the value in the Fourier in its Fourier transform. So somehow some random selected value of its Fourier transform will determine this sparse function. And the reason is simple. If we have a random selected result for the Fourier transform, so if it detects two different results, then their difference will give you 0 for the Fourier transform on this final site. But the difference of two sparse function will be also supported in a small size. Then that means we will have a function that has a small support in the original space and a small support in the Fourier space. And then the inequality set is 0. So in this way, we can recover a signal in a unique way. So that's a major idea. And actually, they use this inequality in various way. Not for more efficient way, they can replace the product as a sum. And then the inequality holds for all of G plus 1 in a high probability. So this is a very important inequality for the signal recovery. Now, let me give an example for a non-abelian group case. So how to define the terminologies for non-abelian groups? So for abelian groups, it's easy to say what's of a function. For non-abelian group, so how do we start the Fourier analysis? To remember the group. The first one is the function on the group. We call it the A algebra since functions are abelian. A is easy to remember. And the second one we call it the B algebra. It's a group algebra. So that remembers the group multiplication for functions that corresponds to the convolution. So we get two algebra. But in addition to the two algebra, we also have two measures. The first one for the A algebra is the discrete measure for the group. And for the B algebra, it's a group algebra. So we can think about this group algebra as an algebra acting on L2 of G, this L2 space. So then it becomes the left regular representation. Let's call it pi. And then for the representation, we have this trace of the matrices. So it takes value 0 at non-trivial elements. And it takes value as 1 or the order of the group G, depending on normalization at the identity. And the Fourier transform, is transformation from the A algebra to the B algebra, so from functions to those matrices, just by replacing the function x as, so we have a function x over the group G. Its Fourier transform is xg times pi g. Pi g is the unitary. And we take this sum. So that means it's essentially the same element, but for xg, we read it as a function in algebra. And we read it as a group element in the B algebra that becomes this sum. That's the Fourier transform. And to make sure this transformator, we can analyze this scalar by the square root of all of G. And then we can write this Dontahue stacked uncertainty principle. We take the support. Then for fx, this becomes a matrix, it's an operator. its support is defined as the rank of this operator. So their multiplication still has a lower bound, that's the of group. And this is first proved by Schlemm. And actually, later we actually use the rank of fx as the measure. It just coincides to be this for this group algebra. There's another way to rate this rank. Namely, we have this trace. So we have operator fx, and we can look at its range projection. The range projection is like kind of the set that this function or this operator supports on. So that's the support of this operator. And the measure is a trace. So we can look at the range projection of this operator and then take the trace. And that should be the right thing to do in general. But in this case, they are the same. So that's the exact rank of the operator. And then this inequality is still true. Now, let's see. This is a very general phenomenon, this Dontahue stack type isolating principle. It's not only true for those group symmetries, it's also true for a bunch of quantum symmetries. So here we mentioned first 3 quantum symmetries. One is subfactor, it's actually more than that. The first one is subfactors. Now we'll talk more about that in this talk. And the second one is Katz algebras. So that is a C-star half algebra. So half algebra is an algebra with a co-multiplication. And the co-multiplication is an algebra homomorphism. And C-star means the algebra itself is a C-star algebra with respect to multiplication. And on the dual side, it's also C-star algebra. And locally compact quantum group is more general. Compared to Katz algebra, we can look at the measure. So Katz algebra for the measure is somehow much easier to study. The modular group is trivial. A locally compact quantum group, the modular group is non-trivial. So it's much harder to study. But somehow those are kind of very general quantum symmetries. And I will tell you soon what is subfactor. And indeed, those quantum symmetries are closely related to quantum theory. When we say they are quantum symmetries, and they are beyond classical group symmetries. And for example, from a subfactor, one can construct a 2 + 1 to reveal topological quantum field theory with certain condition that's crucial. That's a reflection positivity condition. And that's one of Arthur's favorite property. And subfactor ensures this condition on this topological quantum field theory. And this is also a crucial condition for us because that's the condition that provides positivity at the beginning. That means the underlying space is not just a vector space in this topological quantum field theory. It's a Hilbert space. So it seems that we don't tell too much from this Hilbert space, but actually it tells a lot. That means we have, in the product, we have a Cauchy-Schwarz inequality. And why I say it has a lot, it seems that we only ensure one positivity, but actually we have a lot of multiplication. For example, as we mentioned before, we have 2 algebras, A and B. We have multiplication and convolution. And there are 2 different algebras. And both of them has reflecting positivity. And here, in this topological quantum field theory, this one reflecting positivity ensures the positivity for all those kind of multiplications. And there are tremendous multiplications in the theory. So that leads to tremendous positivity and inequalities. So that's part I want to emphasize why we are so interested in analytic stuff on quantum symmetries. Actually, not just the Fourier analysis, but in more general sense. And so far, inspired by subfactors, we are focusing on Fourier analysis because subfactor has a natural Fourier duality. But in general, it should be very important to study those inequalities on topological quantum field theory with this reflection positivity condition. And that's also called the unitary condition. So now let me give you first feeling what is a subfactor and why we call it or why we consider that as a quantum symmetry. The first a factor is simply a Fourier algebra with trivial center. And if you don't like factor, it's fine. You can just take Fourier algebra. Still work for the full theory, but that's our favorite topic. It's a factor. It's kind of simple. And in this talk, we will consider a special type of factor that's called type 2-1. And usually this Marie von Neumann gave us classification of different types of factors. And this is one of them. So I won't give you the original definition, but it has an equivalent definition. That means the Fourier algebra is infinite dimensional. And it has a trace. A very beautiful result of Maria von Neumann said, in this case, the trace is unique. So it exists and unique. It's a unique trace. The good thing is that then this will be the best measure for us to do analysis. And if you want an example for the 2-1 factor, then a very basic one will be the infinite tensor product of matrices. And that's a matrix algebra, but it's infinite dimensional and it has a unique trace. And if you want to be more careful, say if you want a Fourier algebra, then you need to take a closure to this trace. The trace define induce a topology and then applying the GS construction, you get this closure and you get a factor, infinite dimensional with trace. And this is called finite factor. Now, what is subfactor? By definition, it's also simple. It's that you have two factors and it's just inclusion of factors. And the crucial part for this talk is that from this subfactor, as we mentioned, it produced a 2+1 topological quantum field theory. From that, there's an important piece. That's a pair of Fourier algebra, A and B, the A algebra and the B algebra, and with trace. The trace is induced from the unique trace of the factor. So that's a natural choice. And the important part, it gives a free duality, so free transform, the quantum one, quantum free transform from the A algebra to the B algebra. For example, for this factor R, you can take permutation acting on those different pieces, like finite permutation. And you can take subgroups. So any finite group is subgroup of a permutation group. So you can take this cross product action, and then you get a bigger algebra. It's also a factor. And then that gives a subfactor. So the R included in this cross product. And from that subfactor, the corresponding two algebra is exactly the one we started before for free analysis. One is the functions on group, and the other one is and the two measures, the two factor is exactly mentioned. One is the discrete measure, and the other is the trace of matrices. And the Fourier transform coincides with the classic one. So subfactor is a driving machine to produce those interesting quantum symmetries with Fourier duality. Now, why we consider that to be quantum? So in general, we can just consider the subfactor, a pair of factors. One as a R, the other one as a cross product from the action of some quantum group. And sometimes we don't even see this group, but we just imagine there is a group action. And the very interesting part is this the odd of the group in general is described by the relative size called the Jones index. And the size doesn't have to be integer. And Jones classified all possible value in 1983 that it could be the continuous family from 4 to infinity, and it could be quantized below 4. And indeed, the family below 4 has a close connection with quantum SU2. And that leads to the Jones polynomial. So in general, we consider this subfactor leads to a quantum group G arising from this cross product action. And actually, different people give different for this kind of group. Often, hypergroup. But somehow people always think about this kind of quantum symmetry, generally it's like quantum field theory. In particular, this one class carrier CFT. And also in condensed matter, like they consider topological order, they use the categorical structure. That all has a very, very deep connection with subvector theory. So they're indeed quantum symmetries beyond group symmetry. Now, from subvector, what we have to do Fourier analysis is this quintuple, two algebra A and B, and two measure D and tau and the Fourier transform. So that's for us to study the Fourier analysis. And one thing I want to mention is, for the group case, the A algebra is commutative, but here the algebra from subvector doesn't have to be commutative. Both A and B could be non-commutative. This is similar to the half algebra case. Both sides could be non-commutative. Now for the subvector, we have the following uncertainty principles on the quantum symmetry. We call it quantum uncertainty principle. Well, even though this is weird, uncertainty principle itself is a quantum. And here we just emphasize this quantum again to emphasize that the statement is similar. We take it because that's Fourier deal. We take operator and then we compute the support of the operator. So as we mentioned, not support is no longer the rank. It's the trace of the range projection of this operator. And also the support of this Fourier transform. Then their multiplication has a lower bound. It's the order of this quantum group. That's the Jones index. So as we mentioned, the lower bound now is the order of this quantum group with the Jones index. That does not have to be an integer. So that's one very interesting fact. So we still have this inequality, but it's different from the group case. This lower bound is the order of the group. It's an integer, but here it doesn't have to be integer. So in this sense, we can also say this inequality is really quantum. It's no longer the classical integers. And actually, it's more than that. It's more interesting than just that. So first, if we take the group case, then this inequality reduced to Mesh-Lamb's uncertainty principle for groups. And furthermore, if the group is abelian or cyclic, then we get back to Dontahue stack.
So Zhengwei, we've really lost you.
The equality projections.
Zhengwei, we lost you for
Hello? Yep.
About half a minute. So we're trying to contact Zhengwei independently. We're calling Zhengwei on the telephones. Hopefully we get him back.
So
Then.
where did we stop?
Well, we lost you, and then you disconnected when you were discussing this result. But
Okay.
go ahead.
So let me see. Okay. So I'll go through this again quickly. So from subfactor, we have this quintuple, two algebras with trace as measures and a free transform. So we can study the free analysis in a very natural way. And we have this uncertainty principle, saying the support of the operator multiplied the support of its free transform has a lower bound. Similar to the original one, but the lower bound here, it becomes the order of this quantum group, the Jones index. It doesn't have to be integer. This is the quite interesting part. For the group case, this is always an integer. But here it doesn't have to be integer. So in this sense, this inequality. And also, we can recover the group case when we consider subfactor as the one come from groups. Then we do recover their results, their uncertainty principle on groups, and no matter abelian or not. And another very interesting part is we can characterize the equality. The equality holds if and only if this operator X is a backshift of a back projection. So for the group case, what's that? The backshift of back projections are modulations and translations of the indicator function of subgroups. So that means you can take subgroup, and translation just means you move from subgroup to cosize. Modulation means you do this stuff in a dual space. So you take the group elements in a dual that correspond to multiplying a character in the original space. So that's modulation and translation of indicator function on subgroups. So in general, we call that back shifts of back projection. And what's a back projection? So for subgroups, if you look at the indicator function of subgroup, the first is a projection. And secondly, it's also a projection under the convolution. So it's a projection up to scalar under both multiplication and convolution. And actually, there is a bijection between such back projections and such subgroups. So in the general setting, Dietmar Bisch showed in 1994 that there is a bijection between back projections and intermediate subfactors. So that's exactly the quantum analog for intermediate subgroups. And here we are using the this back projections. But here the back shift is in general case, since we do not have group element, so the shift, the definition, like even for definition of cosize, becomes non-trivial. That's the shift on one side. And since both algebra are non-commutative, the back shift becomes very tricky. And considering the order and the different side, there are actually 8 different kind of back shifts for a given back projection. And besides the Dontahue Stark type of inequality, in that paper, we actually also consider the entropic inequality. So we take the operator X, and then we look at absolute value square, even though the operator is non-commutative, but here we consider that as a more quantum analog of the wave function. And the absolute value square is the density matrix. So we consider the entropy for X square and the entropy of free transform square. And the sum has a lower bound. So this is similar to the Hirschman-Beckner uncertainty principle for the reals. And this inequality is sharp, and it holds if and only if X is back shift or back projection, as we mentioned before. And it's worth mentioning that for the reals, the minimizer of the Hirschman-Beckner uncertainty principle are Gaussian functions. So from that point of view, those back shift or back projections play the role of Gaussian functions for those quantum symmetries. And that's indeed the case in various ways. And here we give one example. How do we consider this as a Gaussian function? There's a very beautiful result by Hadai in 1933, this, saying, okay, if we have a function f and a Gaussian function g, and say F is bounded by G, and the Fourier transform of F is bounded by the Fourier transform of G pointwise. Then Harday's uncertainty principle said F is always a multiple of G. This is a very beautiful result and a very somehow distinguished uncertainty principle. It's kind of different favor. And this is true for quantum symmetries. So to set up this inequality for quantum symmetries, well, we need to tell what is Gaussian function. This is even non-trivial for like locally compact groups. And here, the analog is the following. We know the Gaussian functions are minimizer of the Hirschman-Baxter uncertainty principle. So we take those minimizers to be the analog of Gaussian functions. And for subfactors, that's the Best for by projection. So we take this minimizer G, and then we take another operator. We have the following result. If the general operator W is bounded by G, namely, we compare their absolute value, and as an operator, one is smaller than the other. That's how we compare them in a non-commutative setting. But if W is bounded by G, and the Fourier transform of W is bounded by the Fourier transform of G, and then this W is a multiple of G. It's a multiple of the Gaussian. We believe this is the right way to set up this general Harday's uncertainty principle. And actually, there is a deep reason to say why this happened. That minimized entropy is really crucial, but that's not the point of this talk. So I do not go to that direction. And first of all, we can do this in a more general way. So take operator X in this algebra from subvector. Then we can compute its Fourier transform and compute the Q norm. We can compare the Q norm with the P norm. Now, for the Hausdorff inequality, we have this condition P inverse plus Q inverse equals 1. Now, here we release this condition. We consider arbitrary P and Q. Even for PQ, between 1 and between 0 and 1, that means it's no longer norm, but still we can look at this inequality. And then we have this figure. Now for this figure, this K has different values in 3 regions. And the red line is the part we have where we have the Hausdorff inequality. And in general, we can compute this norm in 3 pieces. Actually, here there should be a reference for this figure. This was first computed for groups. I'm sorry, I forget the authors. And then we compute this.
It's in the annals of the It's in the annals of the Linzhe Fourier in 2010.
Yeah, thank you. So they compute a figure for square between 0 and 1 when they have the P norm. But here we extend the figure to the whole area, or arbitrary PQ bigger than 0. And we have this phase figure, and they have 3 different regions. And on the blue and the red line, that's the position for phase transition. And the line at the center, the point at the center is the equality. So that's the 2 norm. So once we have this norm of the Fourier transform, so we consider Fourier transform as a transformation from LQ space to LP space, and then we compute its norm. Then we can derive various other inequalities. And actually, for those inequalities, we can characterize equalizers. So sometimes, most of them are very sharp. And this is an old table. Now we have even better characterizations of the equalizers. And one point we highlight here is for the Hausdorff inequality, the equalizers are Bischeffer by projections. And this is actually an important point between analysis and algebra. We can use inequalities to study those algebraic conditions. So once we have some interesting algebraic condition here, we set up an interesting inequality so that the equalizer give you the algebraic condition. Now, in this way, we can solve algebraic problems using inequalities. And actually, there are examples like that, but still, we don't get much into that direction. In this talk, I will focus on the uncertainty principle. So once we have the norm of the free transform from LQ space to the LP space, like on this 2D figure, then we can take the derivative at the center. So actually, how do we get the Hirschman-Beckner uncertainty principle? The center is the equality. We have inequality on the right line. We can take the derivative with respect to the right line. Then we get one entropic inequality. Now we have this figure for a 2D space, so we can take derivative in any direction. And that gives us a two-parameter family of inequalities. So in that way, we can take the derivative and then we get a two-parameter P and Q. And the entropy becomes the Renyi entropy. It's no longer the von Neumann entropy or Shannon entropy for the commutative case. It becomes this Renyi entropy. And the Renyi entropy is the von Neumann entropy when P goes to 1. Okay. Or if you consider half P for this two norms for x squared, then that's the place for two norms. Now, once we take the derivative, we get this two-parameter family of inequalities. We compute the Renyi entropy, and we compute its free transform for another Renyi entropy, and their sum has a lower bound. So here, by taking the derivative directly, the sum is weighted, but we can modify the weight as we want. For example, the weight can be 1, and we still have a good inequality. Now, this is a general family. From this general family, we can take the limits as special position. So if we take limits as two norm, then we get back to the Hirschman-Beckner inequality. The sum of the two von Neumann entropy has lower bound. And if we take the two limits as infinity for this figure, then we get to the Dontahue-Stark uncertainty principle. So these two very beautiful uncertainty principles actually arise from two different limits of this general Renyi entropic uncertainty principle. So essentially, this is a very general strategy, a unified strategy. How do we get those uncertainty principles? Essentially, we are studying the norm of this free transform from LP space to LQ space. So we consider this F free transform as an operator from LP to LQ, and then we look at the operator norm. And once we know the operator norm, for example, at the beginning, we use the Hausdorff inequality from 1 to infinity, and we use this Planck formula, the free transform preserves the two norm. Use the 2, we can take the interpolation, we get the free transform from P norm to Q norm. And furthermore, we can get general PQ. And then by taking the derivative of this, norm, we can get to the entropic inequality, the entropic uncertainty principle. And then by taking different limits, we can get different uncertainty principles, like the Dontahue-Stark uncertainty principle. So essentially, if we want to get those uncertainty principles at the beginning, it's enough to set up the norm of the free transform. And this strategy works for classical group symmetries and quantum symmetries. So we have done that for subfactor planar algebras, Cassie algebra locally compact quantum group, and recently for fusion by algebras. Another thing related to fusion inspired by the framework of fusion category. And here, one thing we want to highlight is, even though this strategy works in very general science, but the proof of the Hausdorff inequality could be non-trivial. For example, in the subfactor framework, the algebraic definition of the free transform is very complicated. Unfortunately, there is a diagrammatic definition of the free transform. It's a 90-degree rotation of a planar picture. And actually, indeed, in the case of subfactors or planar algebras, both definition and statements and our proofs are pictorial. And we do use the pictures in our proof. So not only we use analysis to study those pictures, the topological quantum field theory, but also in the other hand, we use those topological quantum field theory, means the cobordisms of manifold. We use those topological structure to prove inequalities. I think that is something quite interesting in this framework. And once we have those inequality, then we can run this machine. We get different type of uncertainty principles. And actually, we have done not just those uncertainty principles, but we do other kind of inequalities. We propose the program we call quantum free analysis to investigate those analytic aspects of quantum symmetries. And in particular, for subfactors, we have those quantum free dualities. And the Fourier analysis works very well. And here is our recent paper joint with Arthur, Chunlan, Yunxiang, and Jinsong, published at PNAS 2020. Now, another interesting story is that in recent work of Widgerson and Widgerson is really recent. It's published this year at Bulletin of the AMS. It's a very beautiful paper. They introduced this concept called Harmonic Matrix. So it's a kind of generalization of the free transform matrix, discrete free transform matrix. So they define the matrix using two conditions. One is looking at the transformation from 1 to infinity norm. So this is matrix, so it's transformation from vector space to vector space. And the one condition they want is the bounds of the 1 to infinity norm. This is somehow the Hausdorff inequality. And the other one is the bound for f star f inverse of the lower bound of f star f. So this implies that f is invertible. So based on this two norm, well, one thing you can consider if f is free transform, then this is the identity map. So this is 1. And up to a normalization, you can release the bound of the first one. You can put the number k as a bound for first. So that means if you look at a unitary free transformation, you are looking at the bound of the Hausdorff inequality. So that's similar to what we have in the previous strategy. But here they have this different strategy for the two bounds. And then they showed that using these two conditions, they prove the primary uncertainty principle. This one, the product of the one norm of x and its free transform over the product of the infinity norm of x and its free transform has a lower bound. Lower bound is k. So in our setting, if you consider this as a free transform, then that means this is a pair of Hausdorff inequality, and we multiply the two, and that gives you a lower bound k. Clearly, this uncertainty principle is stronger than the Dontahue-Stark uncertainty principle, because the support of x as this function on set, the support of x is bigger than the one norm over the infinity norm. This is obvious. So this is the inequality implies the Dontahue-Stark uncertainty principle. And that's the primary one in their paper. And we call it the Widgerson-Widgerson uncertainty principle, or this type of uncertainty principle. Not only just on finite side, they also consider this kind of uncertainty principle for real lines. So they take the product of the Q norm of f and its free transform. Q is from 1 to infinity over the two norm. And then they want to understand this value. So when Q equals to 2, clearly this is just 1. The range is 1. And they conjecture that the image of this EQ is all positive real numbers for any Q bigger or equal to 1, but not 2. And their motivation is that they generalize the Heisenberg uncertainty principle, which uses a two norm. They use the Q norm to set up another kind of Heisenberg uncertainty principle. And they want to show these uncertainty principles are inequivalent. So they want to compare the multiplication of Q norms and the two norms are inequivalent, namely there's no upper or lower bound. So they give this conjecture. Well, in recent paper joint with Linzhe, Huang, and Jinsong Wu, now it's on archive, we show that this conjecture is true when Q is bigger than 2. The image is all positive real numbers. But when Q is between 1 and 2, this is not true. This image has a lower bound. And we actually use Beckner's inequality, the sharper Hausdorff inequality to prove this lower bound. But still, this lower bound is not sharp, even though we use a very strong result. This is not sharp. So we ask a very natural question. Between this region, what is the image for this EQF? And actually, we are more interested in the lower bound of this image. So what's the minimal value? What's the best constant? And in particular, which function reach the lower bound? And in Widgerson's paper, they also studied those Dontahue Stark uncertainty principle with a small perturbation. And this kind of uncertainty principle has been considered by Dontahue Stark in their original paper, 1989. So we take a function f, and usually when we consider the function, it may have a small noise. Like if we take a sample, it may have noise. So when we count the support, we want to remove the noise. Then that means when we look at the support, we want to leave a small part. And mathematically, we can define this support up to epsilon, up to p norm, with respect to p norm up to epsilon. So that means we take a smaller supporting set Q, and so that the function on the complement of Q has a very small p norm, means it's smaller than epsilon times the original p norm of f. And then using this support up to epsilon, Dontahue and Stark proved the following inequality, that the support of f and its free transform has a lower bound. The lower bound is there's a missing term. It's the order of the, for the group case, this K is the order of the group for the free transform. And the constant is improved by this epsilon and eta, the small perturbation. And Widgerson, they show that this is true for K-Hartmann matrix, the generalization of the free transform. They still have this inequality. And in Dontahue Stark paper, they only consider 2 normal cases. And in Widgerson's paper, they also consider 1 normal case. Now in our work, we also want to consider the inequalities with small perturbations. So first, we want to understand the concept of K-Hartmann matrix in general framework. Then the underlying symmetry doesn't have to be this vector space, namely the abelian algebra. And the measure doesn't have to be the counting measure. So in general, we say it's a fundamental algebra. And for simplicity, we consider the measure to be a trace. And that's the case when we study subvectors. But in the most general situation, this could be a state or even a semi-finite weight. But for simplicity, and we consider the trace as a measure. And then we have 2 algebras here, A and B, and 2 trace as measures. And then we take a free transform. Now it doesn't have to be free transform. We call it a K transform if the transformation satisfies the following 2 conditions. The first one is similar to the K-Hartmann condition. Second one is also similar. It's the same. The norm of is the inverse of f star times f. And we call this quintuple a fundamental K by algebra. Well, one thing we need to be careful if the fundamental algebra is infinite dimensional, namely the f star may not be well defined. So here we assume the f star is well defined as a joint operator of f. And then from that, we can recover the notion of K-Hartmann matrix when A, B are abelian fundamental algebra with counting measures. And in this way, we'll be able to cover the K-Hartmann matrix and those quantum symmetries arising from like subvectors, those non-commutative fundamental algebras with trace. Similarly, we introduce a support also with small perturbation, but this is slightly different from their definition. And advantage of this definition is the following. This support is continuous with respect to the epsilon. So for the previous definition, the classical one, the support is still the value of some size. We'll take a small perturbation. And here, when we define this new support, it's a continuous function with respect to epsilon. So its value doesn't have to be integer. And another thing that we say this support is a better measurement because our support is smaller than their support when they are comparable. Well, why we say this is better? Because in this uncertainty principle, we can show this in a general setting, this von Neumann K by algebras, that both uncertainty principles are still true. And since our support is smaller than their support, so our uncertainty principle is actually stronger than their uncertainty principle. Now, even for the case of K-Hartmann matrix, this inequality is stronger than their case. And indeed, even for the two-dimensional commutative algebra, we can write down example, pretty random example, and saying, okay, if we compute the product of two support, in our case, it doesn't have to be an integer. It's like 16 or 9, and in their case, it's 4. So our number is actually much smaller than their number. So this is an improvement of this, or somehow a stronger inequality for this Dontahue stack type uncertainty principle. And in addition to support, we also studied entropic one. Also, like in our previous work, well, once we have the norm, once we have the Hausdorff inequality, we first get to the entropic inequality, and then we get the Dontahue stack type uncertainty principle. So here, we also study those entropic inequality in this paper, in this recent paper, for this K von Neumann by algebras. And then we can take a small perturbation of the entropy for X and its Fourier transform. And here, F it becomes the K transformation. And we showed the sum of the two entropy has a lower bound. And when epsilon and eta, when the small perturbation goes to 0, we get back to the original entropic inequality. So this is indeed a generalization, the improvement of our early result. And here, those are this is actually pretty good lower bound, since you see the constant of epsilon and delta only depends on the norm and the two norm of X. So here C is a fixed function, a very good function, but because of the size, I didn't give the formula here. So it's very symmetric and a very basic function, and also the degree of epsilon eta are both 1. So it's just linear bounds. So, and actually there are some additional results in this paper that could be more interesting. And I think maybe Linzhe, Huang can have another opportunity to give a talk on this recent paper. And thank you.
Thank you very much, Zhengwei, for an absolutely beautiful talk. There's so many results here, and I think there'll be very many questions, but maybe I could start by asking a general question. It would be quite interesting to look at the type 3 case when the entropy doesn't necessarily exist and the relative entropy is important. Are there any uncertainty principles for relative entropy?
That's a very good question. First, the answer is yes, even not for type 3 case, even for the finite dimensional case. Actually, we have the entropic inequality for relative entropy. And that's in our paper, quantum free analysis. Well, first the result, again, is non-trivial. And actually, when we define that relative entropy, it's inspired by the early work on locally compact quantum groups. And in that framework, the von Neumann algebra could be type 3. It may just have a weight, even not a trace, and it does involve Tomita-Takasaki theory. It involves a model operator. And the data of the relative entropy has deep relation with this model operator. But just we can make that framework more abstract and do a finite dimensional analog for that, and involve the modular operator as a positive operator in the finite dimensional algebra, and then set up the relative entropy. But if you compare the formula with the locally compact quantum group case, they are actually the same stuff. So first, for sure, there are inequalities for relative entropy. And when we do entropic inequality for locally compact quantum groups, there, the entropy is already a relative entropy. And there may be further improvement for the relative entropy. And I think there's still many rooms to run this machine. And at each step, actually, here I try to make it simple. So it looks like we only have one strategy from like inequality, finally get entropy. But actually, for each quantum setting, there are different difficult parts. And like for type 3 case, we have to deal with this very difficult Tomiya-Takisaki theory. But I think as an operator algebraist, we should not be afraid of that. That should be our favorite topic. And another reason is in recent work, like Roberto Longo or Wilson's work, they do need to study those kind of entropy in type 3 case, and they need the Tomiya-Takisaki operator in an essential way. And certainly, we also want to understand that kind of uncertainty principles or entropic inequality in a different framework.
So thank you very much. I think there are many beautiful things to still be done. And this is just the tip of the iceberg of a new theory. Perhaps other people have questions.
Yeah, I have a question. You refer to sort of minimizers as, let's call them Gaussians, but do you have any ideas what these things actually look like in some of these examples, or so that's my question.
Oh, yes. That's a very interesting question, and actually the phenomenon is very interesting. The minimizer of this entropic inequality. We actually have a conceptual understanding why it behaves like Gaussian, because we are looking at the entropy for a function and its Fourier transform, and actually we have a kind of renormalization process. It's kind of a central limit theory, but the usual central limit theorem essentially takes the convolution of the functions. When we take different random variables, but considering the distribution is kind of convolution of functions, and the limit finally converges to Gaussian. And we have a 2D analog of that. We not only take convolution, but also we repeat this process by taking convolution and the multiplication, because they're Fourier dual. And if we draw the picture in planar algebra, it becomes a 2D lattice. And this process is kind of a renormalization of a very big 2D lattice. And then there is a conceptual reason. After we do the renormalization, then eventually the limit, like for the reals, the limit has to be Gaussian. It has to be something free. But that's a conceptual way to say why we believe this limit is Gaussian, and why we say this has something to do with the entropic inequality. This is another conjecture. Namely, once we do this renormalization, the entropy, this Hirschman-Beckner entropy, should decrease. So the limit has to be the minimizer of this entropy. So namely, if we renormalize the size of the lattice, then this entropy, they tell you something about this lattice model. The entropy should decrease, should be monotone. So those are the limit. Those are the limits.
So what is the hope to prove something like that?
No proof. That's this sounds very reasonable, but so far we didn't find a proof. And not only for the Gaussian, well, then we have this conjecture for the reals. It's a very clear conjecture, but it's surprising. Actually, it's very rare so far, since people have been working on the reals for like hundreds of years. It's hard to find a simple statement without proof. But this is one, and it's related to Gaussian. And another thing is, if we just look at the finite dimensional case, it also happened. So we do the same stuff, we do the renormalization, then the limits will be back projection. That means the limits for the group case, limits will be subgroups. And exactly that's our favorite topic for lattice model, that's the phase. Like for easy model that corresponds to Z2 group, we have two different phases in the limit. And exactly after we run this phenomenalization, we have two different subgroups for two different phases.
Yeah, but how do you see the phase transition?
Yeah, that's another interesting part. Then for the Z2 case, we can compute that by hand. And then we can find the point for phase transition, and that's the critical temperature.
Well, that's used duality.
Yeah, we use the Fourier duality.
So
The reason why that's exactly the critical temperature because we also have the Fourier duality that corresponds to the Kramer-Waldner duality. And since this is Z2 model, it's simple. There is only one fixed point under this duality, Fourier duality.
Yes.
And
So
for the ideal, that's the fixed point for
much more general theorem for other types of symmetries with the fixed point.
And we don't know. And actually, a very basic, but I think very interesting question is, one shall compare this phase transition between Z4 and Z2 cross Z2. They're both order 4 group, but they have different limits because they have different kind of subgroups. So these two figures must be quite different, and they should tell you different kind of physics system, different physics lattice models. But those are all kind of general ideas and no proofs, even no like precise mathematical statements. I think somehow I become partial physicist when I joined Harvard for this year. But I really have a very strong feeling those should be true. This is really a renormalization process. And actually, I can still remember when we run this map, we asked physicists. Physicists said, yes, this is indeed a renormalization map. And when we talk with mathematicians, they said, no, this is not a renormalization map. So we do have kind of a different view when we think about different topics. But certainly the idea seems to be true, but we don't really know how to prove that. No matter it's a finite group or it's reals, both cases are open. And I believe that the fundamental principle behind that phenomenon is this uncertainty principle. The reason is that under the renormalization, this entropy, this joint entropy for X and its free transform joint entropy, it's monotone.
Oh, but that sounds very, very difficult. That must be, there must be some additional hypotheses going into it.
Yeah.
Are there other questions? There's so many interesting things connected with this talk. Are there no other comments? Well, if not, I just want to thank you again, Zhengwei, for such a beautiful talk. And I'm sorry we had internet problems connecting with China, but I hope that we can preserve this connection and that it will flourish in the future. Bye-bye. Bye-bye. See you next week.
See you.